You know, it's really great. It's kind of one-man mission, and you are doing this for 41 sessions ongoingly since the very beginning. Thank you very much. So today we'll be talking about optimization problems in general and about the library, which I came across recently. And I think it's very interesting. It's quite new approach in terms of optimization in Java. When we developers, software engineers, architects, and so on, deal with problems on the business side, we tend to think about solving a problem on a program side. Because it's easy, we are always thinking about solving a problem, adding features, optimizing code base, talking about architectures, approaches, this sort of things. Apparently, these days, there is more and more focus on the data side of things. Why? Because there are approaches that can solve problems with data. And yes, we have this sort of discussions very, very often with our clients, with our product owners. Why you are talking about data? I just want to fix my business issue. And yes, that's all true, but we need to, this is our responsibility, this is our job to sometimes spend time after hours, like we are doing right now, try to traverse the space of possibilities of new technologies and learn something so that we can be better in our job. These days, in AI, the main driving factors are all the machine learning related to neural networks, Bayesian statistics, Bayesian networks. Causality, it's becoming an important thing. But it's all about actually curve fitting. So we try to model the situation in our world in with use of neural network or Bayesian network or something that's actually in a much more condensed fashion representing the true situation. And completely separate kingdom of algorithms is about optimization problems, fixing optimization, introducing optimizer for hard problems. And meta-heuristics are really helping here since 1980s, 1990s in this area. And we'll be talking about those today. Before we crack on with more these days conventional but unconventional way of searching difficult or spaces, we'll go through local search. So these methods were introduced in the 1950s, 1960s. We are talking here about stochastic gradient descent, which is still used. It's powering neural networks. Even deep learning bases on these algorithms. Basically, they are trying to find local minimum. By the way, who is doing machine learning at work today? Who is doing machine learning after work? Okay. That also confirms that those kind of sessions are important. So when you have TensorFlow, for instance, you are running your hello world in TensorFlow with use of multi-layered perceptron. You have to train it, right? So you have a set of data, and you have some sort of topology of the network, and you are trying to condense all the data into the neural network weights, in such a way that this neural network is going to be kind of mimicking behavior as if as if something new about the data itself. And to train this structure, we have to optimize the weights in such a way that they are kind of nicely fitting the problem scenario on a high level of abstraction. Later on we'll get to the more details, but it's important sometimes to traverse these concepts. So local search is still perfectly working set of search optimization methods. However, it has one big problem. If your function is multimodal, so it has lots of bumps, it sometimes tries to explore the local minimum, get to the local minimum and stuck there. So it's not really well solving the global optimization problem. With neural networks, when we have nicely monotonous function, it's a solvable problem. It still can work, although there is still research in this area, and people are trying to address several problems. So how this is actually happening, that organisms evolve trying to adapt to new conditions in the environment. And there were quite a few theories in the 19th century in particular about how the evolution actually works. And only one of the theories in this chart is confirmed. Who knows this theory? Don't be shy. So it's Darwinism. Darwin, the gentleman, Englishman, in 19th century, wrote a book on origin of species, and he won the competition in the sense that he actually, through the observations of the organisms, how they adapt, he was the closest to the truth of how all this is working. And since the adaptation works for organisms, and how come it's not working anywhere else? Yes, it does work. And if you know Harry Knigsberg, who is a freak about agile and lean software development, have you been going through this kind of coaching cycles with your Scrum Masters and trying to figure out how to deal with the software, how to introduce the new products, as soon as possible? And most likely they are building their competences on top of works that people like Henrik Knigsberg introduced, in this case, in Spotify. And the chart here represents this. So, you are building something simple, and then you are evolving it to meet different, more complex criteria of the environment that's created by your product owners and stakeholders on the board somewhere. And even the tools are evolving in time. You have something simple at the beginning, and then you are introducing more and more complexity into a solution space. So the tools are getting better. And yes, in 1960, John Holland introduced genetic algorithm to the science. And since then, we are talking about genetic algorithms. So as you can see, the idea is not new. It's actually not fresh at all, because the theory is known, very well established theory is known since 1980s at least. These kind of algorithms are very good optimizers, general optimizers, in large multidimensional spaces, with highly modular spaces, and very good fit for purpose is the combinatorics issues. So whenever you have an issue that you cannot traverse your problem space just because it's not differentiable, so there are not bumps, but there are some spikes, then genetic algorithms can still work and do the job. That was the theoretical introduction. Do you have any questions about what I've just said? About you would like to explore this a little bit more? There is IntelliJ license to be on today. Okay, let's carry on then. Why genetics? Genetics IO is not that new approach. Franz Wilhelm Stutter introduced this in 2008, or at least he started working on it. And since 2008, he has gone through around 50 releases. The code is on GitHub. You are mostly welcome to join this effort. At the moment, it's quite one-man party, really, which is the biggest, in my opinion, humble point of view, is a problem, because it's an open source project. It's Apache 2.0. It's very well documented, very developer friendly, so developer first approach. So he's writing a code first, then he's adding a little bit of documentation and trying to evolve this application, this library in such a way that this is adopted by the community, which is great. One of the biggest advantages is that it's standalone. It doesn't require any dependency whatsoever. So you are just importing it in a POM, and you have no references, no hidden, no string attached, this sort of things. Genetics is implementing classical genetic algorithms theory. So you have operators like selection, crossover, mutation. It's really important to go through this, because it's a building block of what's happening later, right? So in order to search a potential solution, genetic algorithm is trying to select a quite good solution, perform the crossover, and then add a little bit of randomness to go and mutate of the solution. Is it all clear so far? I got one node, which is fantastic. Thank you. The normal life cycle of the algorithm is we start with initial population. How the initial population looks like, we'll go through this in a minute, okay? Then we are evaluating the population of the potential solutions. And if it is meeting our expectations, thumbs up, we are stopping the process and it's all good. It's very unlikely this is going to happen in the first iteration, right? So we are continuing this. And typical exit scenario is, let's say, a limitation of the permutations that were checked, or the iteration of the generations that we went through. Each and every loop like that starts with selection. So I'm selecting the best candidates. Then I go through the crossover. So I mixed their chromosomes representations. I add a little bit of randomness, a little bit of noise, and I try to evaluate the scenarios again. From the engineering perspective, it's important to understand that the biggest problem that you may have is with regards to the encoding the representation of the problem in such a way that genetic algorithm is going to start working on it. And this is actually the biggest disadvantage of this approach. I will show, I have two examples later on a code level, so maybe you can experience this. Later on, we are building a fitness function, so something that's going to check what solutions are good for your problem and what are not good enough. Yeah? So it's like in real life. If an organism is performing well in the environment, then it's having enough likeliness to find to breed and then have children, a new population of which is a little bit mutated in the sequence. Later on, a normal developer picking up this sort of library is dealing with the library specifics. So the library specifics for in terms of genetics I/O is just a pleasure because it's introducing nicely a stream API approach introducing Java 8, and you don't have to deal with the details of genetic algorithm. You are just playing with a stream of the interactions with which are happening behind the scenes. I will show you later in the code how this looks like. And at the end, you need to start tuning your genetic algorithm. It's quite. It would be extremely great if you introduced GA without any tuning in terms of strategy for the crossover, in terms of the strategy for the mutation. There are many different ways how to improve the working algorithm. Now, the first thing, how to find my representation of the problem. Genetics is, after 10 years of development, I didn't review how France was progressing with the development of this library, but I know this right now with version 4.4 that it has bit strings, real numbers, permutations of the elements, lists of rules, trees, and event program elements. So it can actually crack on with building sub-programs that are solving your problem. Yeah, this is called genetic programming. Are there any questions? Okay, I measured 5-second silence, so I will carry on. Going down to the architecture of this library. The domain model consists of value objects, typical value objects, immutable classes or immutable objects, where at the down of the hierarchy of the representation we have gene. By the way, those are snapshots taken from France's documentation. It's in PDF. The first click on your website, there is a PDF, 150 pages. Everything is there. Gene, later on a chromosome. So chromosome is potentially a sequence or a tree of genes that are representing a potential solution to a problem, like like an individual in a population. Okay, speaking the biology language. Later, the genotype is containing many chromosomes, and phenotype is something that's actually gluing together the genotype, so the representation of the problem, together with the fitness function. So France's library is able to call the fitness function, check how this genotype is performing in an environment, and give the value. And later on, the sequence of the solutions or individuals is just a full population in a given generation of the problem. So in a single iteration of the genetic algorithm. Is it all clear? Am I not going too fast? Okay. If there are any questions, please raise a hand or just introduce immediately. Operation classes. So there are two important operation classes, selectors and alterers. Selectors are representing the selection strategies. There are many, as you can see on the list. There is selection of tournament, elite. I will explain you one of them. So tournament, we are from the generation of potential solutions, we are picking randomly, let's say 5 of solutions, and we are checking which has the biggest or the lowest fitness function, yeah? Depending whether we are optimizing, seeking maximum value or minimal value. Yeah? For the argument's sake, let's say we are optimizing, seeking the minimal value, yeah? The hole somewhere in this multidimensional space. So I pick up 5 guys from the generation, from the population, and then I find who is the best one, and this guy who is the best is staying with me for the next generation. Then I run, and I do this for entire population. I select, let's say, 20 out of 100, and I have the best 20 of the best of 100 guys that were, this generation present in my solution space. So this is tournament. Elite, for instance, is, and you can configure this. You can play around with the percentages and probabilities here. Elite is giving a chance to always find, for instance, 5 the best individuals in a given iteration of the generation, and leave them on the side. So it's a way to potentially very quickly find really good solutions, but sometimes you may be missing, you may be not exploring the space enough. So it's always a dilemma whether to exploit a position that you are in or explore this further, right? You are in these dilemmas as well. Angular and CSS and Oracle a bit, and you could be really good in this because there is so much to learn, but why not checking something else, right? Like Jenetics.io. So you are exploring the space. Sometimes the spaces are very, very big, so we know that we are not going to explore them for sure in a lifetime of a single generation, right? So, but it's all the tuning that we need to perform in our lives as well. Alterers, it's a method that or the group of methods that are introduced, that are dealing with mutation and recombination. They are actually helping to control how the algorithm is going to traverse the system, the problem space. And that's why it's important to kind of be aware of those bells and whistles in order to tune the algorithm later on. Then very quickly there is an engine, there is a package in the library, and this introduces 3 elements. Engine, something that set up the context, like Spring context, of the evolution process. It's immutable, so when you code it and you start your process, you cannot change it at all. If you wanted to modify something, then it's the evolution stream, and this is something really nicely introduced because you can interact with the algorithm. You can introduce limits while it's running. You can pick some details for the statistical, for the debugging purposes. I will show you in a minute. At the end, there is an evolution statistics class, and this is actually introducing debugging facility. Shortly speaking, Franz, I hope you forgive me. Examples, yes, this is the magical moment. We have 30 minutes of going through code and two examples that I prepared. Which way you prefer? To be very synthetic and follow the slides, or go down to the code level? You need to tell me. Second one. I will go through the slides anyway, just because I sensed, there is a little bit of unsureness, what to do. But we'll go through code too. So first problem, Rust region. It's a nice function. It's nice because it can be highly multidimensional. So at the moment you see 2 dimensions, right? Here and here, and the value in any point of this square. And the problem here is to find the minimum. So if I had a local search problem, local search algorithm, it could find, yes, quite a lot of quite good solutions, but it would easily stuck in one of the holes here. And it's a nice function because it can be scaled to 1,000 dimensions, for instance, easily, without any problem, in 3 lines of code. So this is the 3 lines of code, or maybe 4. Yeah, depending on how nicely I organize the brackets. But the fitness is actually going through this calculation for each of the arguments that's given in a vector, right? In an array. So for our graphical representation here, it's just 2 dimensions. So we'll have the array of 2 elements, right? x1, x2. Here is a code which is prepared by Franz. Maybe I extended this a little bit. So we have an engine. We are creating the context of the algorithm. We are running a builder method, which is linking, with use of the Java 8 feature, a static reference to the fitness method defined here. It's running a method to creating the boundaries and of the problem space, and the initial representation of the genome. It's random. No one knows where it starts. We define this problem with population 500. So there are going to be 500 representatives of potential solutions here. Okay, so on this space, I'm going to introduce 500 elements, 500 points that are going to check, how the life looks like. What is the value of my fitness function, of my adaptation to the environment? I give a hint to GA. We are searching for minimum value. And I am defining 2 alterers. There are default values of mutator and I think mean alterer is used by default as well. I picked up, or actually I copy-pasted from an example of Franz, mutation of 3%. So 3% in your genome details are going to mutate. So randomly, change during the loop of the single generation. And then I built the entire model, and from this point on, I cannot change it. I'm introducing a statistic object, so it's weaving into it's weaving into the stream, and I run the algorithm. So it's trying to find out the best potential solutions out of 100 generations, because I created a limit of 100. And in case it stopped it happened that for 7 subsequent tries it had exactly the same result, you are free to stop as well. Okay, so I will show you how this all works. Okay, so our fitness function, and in main I have exactly the same as I showed you. And I'm running the algorithm right now. Okay, it was very quick. So for these parameters, and it was 500, population of 500, a limit of 100, it required 12,000 tries in a space to make sure that it's finding the best solution, which is the minimum. And we know that this function has a minimum in 0.000000, depending on how multidimensional the space is, and the minimum is 0. But this algorithm doesn't know this, right? Because it wasn't taught the representation of the function. And in fact, in 3-dimensional space, it found something quite close to 0, with quite close to 0 value. All that took him around 5 seconds. I have the exact figures later on, because I run a few experiments like that. Are there any questions to the code side of things? Then I will ask a question, and probably I will get the no, it's all joke. Common problem is, okay, this is just a maths from university, nothing that's standing next to my problems as an engineer, as a developer, reporting to my product owner how to introduce a feature. And that's a common question. And I picked up a new class of problem, something that I'm personally working on. And there is a job scheduling problem. I'm sure you are running batches in your systems, right? Who is running batches in a system? Most likely you are going to get the license for IntelliJ. So imagine that you have quite a lot of batches. Yeah? In this example, colorful table, you have just 2 classes of 2 classes of batches, right? Something that is actually using resource 1, and something that's using resource 2, like CPU and IOs, or a database, or a call to very expensive third party. Anything you can imagine. So when I run one of these batches without anything else, I got quite low utilization of my resources. Second, with the similar situation when I run batch number 2 of the same class. Low utilization. However, when I have 2 batches running together, like B2 and B4 of a different class, that's a little bit more expensive in terms of utilizing the second resource, I got a little bit higher utilization, and I need to be careful here, right? If I run one more batch of class 2, then I would be in trouble. But nothing happened. Everything, nicely utilized my infrastructure. So in cloud, environments, it's all we need to do, because we are optimizing to use, the maximum of our resources that we are paying for. But next day, someone ran 2 batches of the same class. Again, higher utilization, nothing happened, no drama. Everything finished in the same time as previously. However, they were running in the same time. We learned out of this something. So we are able to, by observing the environment, to figure out what is the typical utilization of the resource for my job. So this is a search problem. Yeah, I can find from the environment that's quite complicated, unknown, changing, because we are running releases. We are running new features, introducing new features to the system, etc. But that was all successful until someone ran from application support side, run 3 batches of the same class that was perfectly fine, running yesterday, but today it's actually running longer, and it's utilizing full of my resources. It's introducing contention of the resources. Anything else is getting stuck. Yeah, I'm sure you were going through this kind of problems, right, in the past. So we try to avoid such a situation. So what to do? We can reschedule those batches. We can suggest, or an algorithm can suggest application support. Such a situation is going to cost you not only longer execution, so you are not deliver the final result on time, but you are going to impact other features that are running. How come something is going to know what's going on? Well, it can know for the data of the system that's running, and it is searching the space. So it's another optimization problem. So in this example, we have 2 optimization problems, and I implemented a code to solve the second scenario. How to reschedule the batches in such a way that they are not overlapping with each other, or they have minimal impact on the resources that they are working on. And absolutely tragical situation at the end of the day 4. We are running everything in one go, and that's why we are having 15 squares highlighted, although we just need to have 9 of them. So we are losing time to deliver something, which may be critical in certain conditions, right? Was it too quick? Shall I repeat something? Are there any questions? That's a very good question. Thank you. We'll have to choose who is the winner. It's going to be a hard optimization problem. We need to find out a good representation of the problem for the genetic algorithm. Perhaps there are many ways how to solve the problem, but I introduced something that I hope is going to be easy to understand for you now, right? So instead of this matrix of colorful ones and floats, I have a table that has 1 and 0s only. So this is integer array. Each of the rows represents a batch, as before. And each of the columns represents different time slot. So I created 24 time slots just to be closer to the real world and reflect the amount of hours we have in a day. But it could be any number. And in this example, I have 6 batches. Who knows how many solutions of the problem I have here? Okay, so we'll go through this slowly. So the first solution is right now. My starting condition. It can be very good actually, but there are a few things that we could change here. For instance, on a third law, we could shift these ones to here, so they are not overlapping with the second row, right? So this is the first try of the optimization. If I do this, there is going to be a second solution. So if I was doing this brute force systematically, I would have to shift each and every batch in this array 24 times, and then try to deal with another batch. But I would have to shift one here and then repeat exactly the same old scenarios that I had before, and then 6 times of this. So I have a search space of 24 to 6th power. And I calculated this, it's around 191 million of potential solutions. Yeah? Now, calculating how the batches are overlapping can be quite computationally expensive. And that's actually, in the whole optimization scene, the biggest problem. We really sometimes want to reduce the amount of tries, of the fitness function checks, the calculations, because they are the most expensive. Who heard about reinforcement learning? Thank you. So in reinforcement learning, you are traversing the environment, adapting to the conditions that you are finding, and building your representation of this environment, right, of this situation. It's a kind of optimization problem too, but it's different, just kingdom of sub-kingdom of machine learning. We don't want to talk about it here, but I'm just highlighting why machine learning here, because in machine learning, in reinforcement learning, it's really dramatic sometimes to send an agent and go through that environment. It can take hours. Okay, let's go back to our example. It's really, really simple. Are there any questions? Okay, so to calculate, my fitness function, I created a function, a class, but it's boring because it's nothing in common with machine learning. It just takes the potential solution vector, and it checks what is the value of my function, my fitness function. If you want it, we can go through this too. But then I set up a population of, let's say, 50. Same mutators, alerts, boring to death, and a limit of 1,000 iterations, right? So we have 1,000 generations of 50 guys to be there, experience the fitness function, this environment, and to find something that's that has the lowest value. Why the lowest value? Because I am really interested in the lowest level of the overlaps, and this is how my fitness function works here. This is just to back up that this is a real world problem. So this is a hypothetical problem space of batches running in a given day. Yeah, so there are zillions of classes, around 50 or 70 classes, and quite a lot of runs of such batches. So it can be a big problem, really. This is a snapshot of previous representation of this section, but only 4 hours, and all the batches were sequenced in such a way that they are, easy to be seen. I hope you can see the dots. The dot is a batch that's running. Yeah, so you can see that sometimes there are quite a lot of overlapping batches. And evolutionary application support or administrators in this particular systems found out that actually short batches can be run together. No, there is no harm. But longer ones, they are difficult because it's difficult to introduce different time to solve the puzzle. So I see this problem here as quite well organized batch framework run and execution environment, right? So there are not that many overlapping batches. If after a particular release we introduce a problem in let's say execution of this class of batches here in this column, we would see a shutdown of the system, because if I run 30 instances concurrently of something that's far less nicely using resources, everything would stop. Okay. And and this is a moment where we need to realize this technique, and I don't know, something strange is happening whenever I'm closer to this space here. So this is my, can you still see the code, or shall I go to demo mode? So it's exactly as we experienced. There is a table. This table is linked to my class that's giving the fitness function, and I'm running this time a little bit more kind of extended setup of the genetic algorithm, but it's only to allow to see what's happening, right? So there is a little of system out print line and this sort of things. I also introduced a method that's weaved here into a pick method of the engine stream. So after every single generation, we will see something, what's happening inside the generation, right? To see a little bit of true situation. Okay, I will run it. Are there any questions? Okay, and we had a 24,000 tries to find the local minimum. We spent 330 milliseconds on actually trying to find the best scenario. Just because engine object in genetics is immutable, the context is immutable, the streams are based on something that cannot change. Therefore, I can introduce as many threads running the genetic algorithm I can. Unfortunately, at the moment, there is no direct support for Spark, Apache Spark, but Franz has it in his backlog. I think he's just waiting for someone to say, it's really needed for me, can we do something together? So if you are running your problem, anything with Apache Spark, that's a very good moment to be dragged into the scene. So this machine is running quad i7 with hyper-threading, so most likely 8 threads were executed to go through to the space, and there were 24,000 tries. What else I can learn? Okay, and that's my best. Sorry, I'm still running a Austrian function. Sorry, my bad. Okay, now a little bit more interaction. It's not that boring anymore. Okay, so as you can see, I set it up with a limit of 1,000 generations, and unfortunately the algorithm had to have this 1,000 generations to run. Each and every generation was reported in a log, giving me the worst candidate in this particular generation and the best one. And as you can see, for some time in the last, let's say, 50, somewhere at the end of running it, nothing was actually changing in terms of the best candidates. So if I had a limit set up to run 25, finish your algorithm when you cannot finish before, when you cannot find anything better in 25 tries, 25 generations, then I could burn a little bit less coal. It started with quite high values of worst solutions, and over time it improved. It improved and it found the lowest value of 88.9. So what does it mean? That the algorithm suggests to leave as is row number 1. Nothing can be optimized here. Leave alone number 2 as well, because it's nicely not overlapping with the first row. But shift the third row of 6, so somewhere here. Then shift number 4 by 2, so somewhere here. And the longest one, the last one, needs to be shifted by 8 positions, so let's say somewhere here. So it's actually nicely, it's suggesting nice, not overlapping conditions. And 88.7, it was actually the best solution I was able to find running this algorithm in last, let's say, 3 days. Apparently the manual setup, so something that I was suggesting this to solve the problem, gave a little bit higher value. I made a mistake, so it's something even in such simple solution worth to be noted. Okay, but let's go and solve something quite difficult, right? So here in this CSV, I have a table that I showed you on the presentation. This. So here we are dealing with 140 time slots and 120, almost 420 jobs. So this gives this figure power to this figure. I wasn't able to run the computation on Google. It started searching the string. It's quite a big number. And I will just run it for you. Okay, it runs around 100 seconds. I also compared genetic algorithms, genetics library with particle swarm optimization. It's a little bit different approach. Well, not a little bit. It's quite a different class of optimization algorithms. I was explaining this on the last on JDD. It's very, very powerful approach, but in this particular problem, apparently GA is better. Although the execution times tends to be bigger for this simple problem, it's 700 milliseconds. It finds better solution, slightly better candidates. With big problems, with complex scenarios, the situation is opposite. It's running half the time. And it's finding far better solutions. So actually, a PSO, under these conditions of 100K evaluations with a population of 100 units and iteration limit of 1,000, didn't give me any benefit whatsoever with respect to the human proposed solution. So obviously, if I gave a little bit more computational power, it would solve the issue. But maybe it's not enough exploring the space. It's a huge space. This number is really difficult to imagine. Are there any questions? Just one thing. If I was potentially implementing a solution, I could implement a simple solution, a solution to the simple problem in real time. So imagine there is someone who is clicking on in an application, and in 500 milliseconds, 700 milliseconds, I could propose a little bit better setup. So it's real-time interaction. When you are running optimization problems, it's really, really important before you start tuning it to realize what's happening. On the left-hand side, I see a scenario that's showing me actually fine, quite good execution. So the algorithm is sometimes making mistakes. It's going back, but it's over time it's producing better solutions. The blue one is the maximum of the generation, the best breed, and the green is average. So in a time of, let's say, 100 or 200 generations, it found a quite good solution to the problem. This chart represents a solution to minimizing urban traffic mobility, and it's actually showing that the fitness function was performed. This is an opposite scenario. We are trying to find. The microphone isn't working. No problem. One. And here, researchers were presenting something that is surprising, because in the middle of the generations, they started losing something. So it's really important to, for the debugging reasons, to visualize the execution. And a little bit of literature, Jenetics. There is a book written by the user manual by Franz Wilhelmsdotter, a very good lecture on topic, 150 pages of solid foundation for development. And then Zbigniew Michalewicz, genetic algorithms and data structures, something that 15 years ago on study I was going through, and still present, and still a great literature. Introduction to Genetic Algorithms by Melanie Mitchell, and something in Python world, if someone is losing patience on Java or something. In machine learning, has only runtimes in Python. Something relevant, but I have to say that Java is doing quite well in optimization scene still. And that would be everything for today. Thank you very much, and I'm open to questions. There is JGAP. I have it for demo, because I was sure that this kind of question is going to be shot. And I will show you a simple example, right? This is how these guys call it, a simple example, a kind of hello world. And it has, it's building, configuration, setting up the fitness function. It's fine code. You can work with this. I didn't run any experiment in terms of the power of the library, because I do not see a valid reason to do so. If the GA is working as intended, then the biggest load on the execution time is having a fitness function here. So there is no point of checking two GAs for the problem that I introduced for the demos issues. But it's just longer code, and look here, you have to introduce a for loop to run your generations. So maybe, yeah, maybe, but I'm not aware of. I was checking this. Maybe they have something, hidden. I doubt. Maybe they are optimizers. There's actually, quite good area of problems that are not that typically solvable by meta heuristics, like particle swarm optimization, like genetic algorithms, and previous approaches like simulated annealing. There are different class of optimizers, and I know that these guys are using solutions of Microsoft, proprietary, no open source, this sort of things. But even for quasi-scheduling problems too. Meta heuristics scene is quite open source. Because the theory is quite well established. There were zillions of bio-inspired solutions to meta-heuristic problem on a high level of abstraction, and perhaps even too many of them, because even 10 years ago it was quite crazy. Every single year there was a new idea about something, how to solve the optimization issue. Yeah. Ideas like BAT race optimizers, or Yeah, there were a few crazy ideas. I'm not saying they are wrong or bad. It's just, interesting, to see that there are more and more abstractions from the real life trying to be brought into the area. So I prefer genetics really than running, for loop and dealing with the genomes somewhere here. JGAP was the active development finished in 2009, I think, or 2010. I would have to check it now. So, but 9 years ago, right? At least 8. So this is a competitor in Java. Are there any questions? Okay, I measure 10 seconds silence. So thank you very much. I hope you started your weekend well, and let's see next time perhaps on next JDD or another conference. And once again, thank you, Marcin, for keeping this group rolling. Thank you. Jakiś after party?